Thank you. Hey everyone, I know it's kind of late in the evening, but hopefully this should be a pretty fun, interesting session. Maybe I'll help you feel better about fine-tuning versus RAG at the end of this, I don't know. But anyway, just to introduce myself, I'm Arnav. I'm a machine learning engineer at Predibase. I lead a lot of our fine-tuning and inference sort of efforts at the company. And the talk today is about how can you fine-tune and serve open source LLMs that rival closed source models. So think, OpenAI or Anthropic or here. And my hope is to essentially leave you guys with an idea of where fine-tuning really fits in the LLM sort of ecosystem. And also leave you with two open source tools, one for fine-tuning and one for inference, that you can use if you're interested in actually getting open source models in production, either for better quality or for lower cost, it depends. Cool. So with that, I wanted to start with this chart. For those of you who can't see it, essentially what you have is on the y-axis, you have average performance on 30 different tasks. And it's everything from classification to summarization to code generation, math, science, the usual benchmarks. And on the x-axis, you have a bunch of models, both open source and closed source, just 3.5 and 4. And what I wanted to show you with this chart is pretty much what we all live and believe. Closed source models are really, really strong out of the box. They consistently beat open source LLMs again and again and again across really wide variety of tasks. But what's really fun about this is that when you fine-tune open source LLMs, the narrative changes completely. What we've consistently seen across 20, 30, 40, 50 base LLMs is that when you fine-tune them on the same tasks, they consistently match or beat closed source models very significantly. And the red bar is the sort of average performance SIP that you get when you do fine-tune these models. And what's also really fun about this chart is that these models are just 7 million parameters. There's even larger models that will give you even better performance. But what I want to show you is that you can get away with really small models. To sort of prove this out, we actually, to put our money, out our money, I guess, whichever way the phrase goes, we actually fine-tuned 30 models using this from 7 billion. We benchmarked against GPT-3.5 and GPT-4, and we plotted the average performance improvements across 30 different tasks that are pretty common that people might want to do in production. And you can see anywhere between 1% lift and 91% lift relative performance. And improves with better open source models. And also, if you just want to get a feel for what fine-tuned model performance is like, you can go to predibase.ai/LoRaX. It's a live demo that runs 25 models concurrently with almost no latency degradation. And I'll talk about how we do that in production as well. So hopefully, this sort of motivates fine-tuning where it fits. The truth is that I think closed source LLMs are great in production at the starting point. They're really good to get value out of LLMs and see if you can actually do something useful with it. But the truth is that most people actually want to put LLMs in production for very narrow, highly specific tasks. And that's where fine-tuning excels. So just wanted to leave you with that. In case you're curious about use cases for fine-tuning, there's classification, code generation, summarization, sentiment analysis. In fact, I would even say there's fine-tuning for that. Specifically improving the RAG model performance through fine-tuning, so they're not so much like one versus the other, but more synergistic in that they can help each other. You can even do fine-tuning for hallucination, to reduce those. So many different things that you can do. So with that, hopefully you kind of see the value of fine-tuning. And we can talk about how do we actually get these fine-tuned models to production. So the first starting point is how do you even fine-tune an LLM? And I just want to do a quick show of hands. How many of you have fine-tuned a model at all? Nice. And how many of you tried fine-tuning an LLM specifically? Cool, actually more hands than I expected. That's great. I'm going to do a quick introduction to fine-tuning. So traditionally, the fine-tuning process is very simple. You have a model. It has some weights. And in deep learning, we have this notion of a forward pass and a backward pass. So during the forward pass, you take rows of data, pass it through the model, and it generates some predictions. And during the backward pass, we essentially compute the error or the difference between what was predicted and what was the ground reality. And we use that to update the weights. And usually that means you update all the weights in your model. However, in the LLM world, this is actually very cost prohibitive because you have 7 billion, let's say you start with a 7 billion parameter model. For that, you need pretty much between 4 and 8 A100s to just get something going if you want to fine tune everything. So super expensive, very slow, just kind of painful. And there's also other pitfalls. For those in the know, it's catastrophic forgetting, where the model forgets everything that's learned during retraining. It's not something we want. And so this is not the way to fine tune that I personally, I mean, if you have the money and the budget, absolutely do it. You will get a better model, but there are better ways to do it. And with that, last year, this is not a new idea, but last year, there was this new method that came out called low rank adaptation, or LoRA, and it's a parameter efficient method. What that means is that you actually just fine tune a very small subset of the model's weights, usually between 0.1% to 1% of those weights, and that is good enough to get you very high performance. The way it works is very similar to what we had before, but the difference is that we no longer fine-tune the base model. We freeze those weights, we don't touch them, but we surgically insert some new weights and just update those during training. And the architecture here is very important. So if you notice here, there's this A matrix and the B matrix. When you multiply them, they have the same shape as W, so you can do summation operations on tensors. But during the backward pass, those are the only ones that are updated. So your learned model weights during fine-tuning are just A and B. You don't actually need the base model at all. And this will be useful for when we talk about inference. And in terms of performance, it turns out that even though we're fine-tuning such a small set of weights, we actually don't lose much. So this is from the original LoRA paper. You'll see that on 2 base models, you get roughly the same performance as full fine-tuning. But if you look at the number of trainable parameters, it's a very small fraction, usually between 0.1% to 1%. So really fast, really cheap to fine-tune. For those of you who don't believe me, on average, it costs less than $8 to get a fine-tuned model that is level quality. And it's because you can do LoRA-based fine-tuning, which gets you very far. It's not perfect. People are doing research and improving it further, but for 95% of use cases, it does extremely well. And so with that background, let me introduce you to, So there's also another optimization that you can throw in called QLoRA. Also got very popular last year. And it was especially popular during the sort of like CPU shortage period when no one could get A100s. And it's this idea that you can compress your base model weights because you're not actually using them for, they're not actually getting updated. And you can compress them by a factor of up to 8x. What does compression mean? Normally weights are stored in 16-bit or 32 bits, but you can actually drop that down to just 4 bits. And since the base model takes up most of the memory, you actually get loss saving. So with QLoRA, you can actually fine-tune a 7 billion parameter model on like an RTX 3090 or a T4 GPU, which is available for free on Colab. So pretty game-changing if you don't have the resources, but if you do, probably just do regular LoRA training, whatever. And with this, now I can introduce you to an open source framework that we call Ludwig. It's a declarative ML framework that was started at Uber by Piero, our CSO. And the idea is very simple. Instead of spending time writing complex learning code that is error prone and hard to experiment with, what if you just define everything as a YAML file, or your pipeline as a YAML file, put that in state models to that. So all of the stuff that I've talked about, a lot of moving parts, can be distilled into roughly 6 lines of the YAML file. You can specify model type as LLM. You can set your base model to be any open source base model. We support them all. And you can specify adapter type as LoRA, and quantization is 4 bits, and it's just that. So write your config file. There's all sorts of configuration options. This is probably one of the smallest. That will get you pretty far. And then you import the Ludwig model, you pass in your config, and you call .train. And beneath the surface, this essentially pre-processes your data to pre-processes all of your data to actually be ready for fine-tuning. It actually starts training. You will see checkpoints. You will see a really large scale of metrics that are produced. Makes it very easy to spend and leave it, and then you come back like 3 hours later and it's kind of done. Would encourage you guys to try, and I'll leave a link probably towards the end of the deck. But through this, it's pretty easy to get started with fine-tuning. It takes away all the hassle of writing all the code yourself. You can focus mostly on experimentation, and you can train hundreds of fine-tuned models. One may ask why you might want to do that. We can talk about that. But yeah, this is the framework to train. So let's say you train your first production LLM, and now you actually want to take it to production. This is actually where most teams have a hard time kind of getting past the fine-tuning and customization barrier. And so for this, we also built a whole new tool for inference that's very optimized. And I'll talk about that next. So traditionally, the way people do deployment in production, historically the way they've done it is that for each model that you have, base model or fine-tuned model, you essentially spin up a GPU pod, you host your weights there, and you'll do this for each model that you want to put in production. In theory, there's nothing wrong with that at all. It works just fine. However, there are, in my opinion, two problems with it. The first is that your costs scale linearly with the number of models you want to put in production, right? So let's say you want to put 10 models, you're paying the cost of 10 GPUs that are always running 24/7. You want to put 100 models in production, it scales by a factor of 10 from there. And the second is that the reality is that in production, when you have a lot of LLMs, not all LLMs get the same level of traffic. So most of your models are just sitting idle in production. Some of them have high traffic, so there's burst capacity that's needed. And so really this is extremely wasteful, requires way more orchestration. And the fun part is that most companies have an ML platform team that's usually sort of like the bottleneck in getting models out to production. So you're going to have to talk to them saying, hey, I want another EC2 instance to put this model in production, which you will usually get pushback on. This is what I've experienced at most of the companies have been at before. So can we do better than this? Yes. And this is why we created LoRAX with the fun LoRAX guy. Stands for LoRa Exchange, and it's a way to serve hundreds of fine-tuned LoRa adapters for the cost of one on a single GPU without sacrificing on latency or throughput. And what am I trying to do for the remaining, what's that called? Oh, am I going too quick? Okay, so I'll slow it down here. 15, cool. So what I'm going to do for the next 5 to 8 minutes is talk about LoRAX and how you can how we actually went about building this sort of infrastructure that lets you do hundreds of fine-tuned LLMs on a single GPU. And the core idea starts at how LLMs actually work with the surface, or how you put a model like this in production. For those who can see, so typically you have, if you spin up like a Kubernetes pod, or you might use a different orchestration service, and then you spin up like a GPU resource, you load your model weights in memory. In this case, a base model and the LoRa weights loaded in blue. And you put a server layer around it so that you can receive requests and respond back. To make this more interesting, you might add a request queue in front so that requests can keep coming in. And while you're fulfilling certain requests, the other requests will get dropped. And then you finally have a router layer that actually takes requests off the queue and then responds back and does some level of batching and orchestration. This all makes sense, but it's kind of inefficient for the reasons I talked about before. And so with LoRAX, it's a bit more interesting, and we do a couple of very interesting things. So the first is that LoRAX takes advantage of two properties of LoRa-based fine-tuning, which I talked about earlier. The first is that most people pick a single base model and then fine-tune many models on it because they pick a strong base model to start with. The second is that LoRa weights are only 0.1% to 1% of the weights, which means that in terms of like disk space or in memory, they're usually in the order of like 50 megabytes. And that is actually very useful because what it lets us do is dynamically load these weights into memory, use them for a request, and then offload them strategically when we need. And so LoRa is based on this principle, and that's where we're able to do this. The idea here is that each LoRa adapter that comes in with the request, if it's new, we create a specific request queue for that LoRa adapter. The reason we do this is that we want requests. So every time a LoRa adapter is already loaded in memory, we want to be able to fulfill all of those requests. But in the background, let's say someone prompts user 3 in this case, prompts a new LoRa adapter, we can load those weights into memory in the background while still fulfilling all the requests that are coming from other users. And so we're able to dynamically load it on, and when there's no request, if it's idle time or too many adapters, you can offload it strategically. And as you can imagine, so it's user 3, you might add user 10, you might add user 50, you might have user 1000. And if each user comes in with a unique LoRa adapter, you're going to run into a GPU bottleneck where you don't have enough memory to load your model weights, your KB cache, and also the LoRa adapters. And so For that, we built in a new mechanism called multi-tier caching. And the idea is that you can smartly unload, offload, and use memory hierarchy to reduce essentially the overhead of adapter loading and also of memory overheads. And to keep it really simple, stick with these scenarios that you might have, right? Actually, for those who are not familiar, GPU memory is the fastest way to get, do computations, and it's where we want to push all of our computations to produce outputs. CPU is slower, probably wouldn't want to use that, and disk, you can't really do any computations on it. So let's say a request comes in, and I already have a LoRa adapter that's in memory. If that is the case, I can just fulfill that request and respond back. Everything works just fine. The second scenario might be that a request comes in, I have some memory in my GPU, but it doesn't have the LoRa adapter. So what I can do is download it to disk and then read it into CPU memory and then preload it into GPU memory. And while that's happening, that request, the actual request for that adapter just sits in its queue, and once memory is loaded, we can fulfill it. But the third scenario might be GPU memory is full, a new request has come in with the new LoRa adapter, and you need to serve that. And that's what we do, like a couple of things in parallel. You'll offload in LRU cache style with these recently used adapter to CPU memory. If that's full, you do it to disk, and then you read and reload the other adapter. So it's a very fluid dynamic system that's always happening. But what's really cool about doing it this way is that you never have to think about loading it or offloading it. You just send a request, and it's very quick. Usually loading an adapter takes only about 200 milliseconds in real time. And if you think about LLMs in production, usually the response latency or total response time is milliseconds. And the cost also gets amortized if you were to send a request with a really large number of output tokens or many requests to the same adapter, because it stays in memory. With that, the last thing that I want to talk about is that we did that's very unique is how we actually do fast LoRa inference. So if you think about it, logically, LoRa inference should not be very fast. We're adding in new weights. There's more matrix multiplication. That means it should be slower, and it is. And you might have LoRa adapters with different ranks to those familiar, which means there's more complexity in actually pushing requests out. But and there's clever batching things that you can do. But just to keep it simple, we use this CUDA kernel called the SGMV kernel. It stands for Segmented Gather Matrix Vector Multiplication. Fancy name for a very simple idea where the way LoRa computations work, if you remember my original figure, is that there's a W, there's an A and a B. You can set inputs to both and then add them at the end. So you can parallelize doing the W computation, and you can group and parallelize the A and B computations. And by doing that, what we found is that as you scale the number of LoRa adapters, your throughput or overall throughput from the system has almost no degradation in performance, which is pretty nice. And if we do the opposite, which is sort of like latency, so time taken to produce a number of tokens, you also see that the time per token, if you will, stays nearly linear as well. And so we built a lot of these cool things. It's sort of all available in the open source. I also wanted to talk about VLLM. So LoRAX is built on top of PGI, which is some Hugging Face text generation inference. We built on top of it because PGI was one of the earliest frameworks out there, and people use VLLM in production a lot. LoRAX is just as competitive on performance, but the cool thing at Predibase, because we own both the fine-tuning story and the inference story, is that we can do some pretty clever things at training time that help improve throughput at inference time. And so actually on Monday, we'll be announcing this thing called the Turbo LoRa adapter. It's a new sort of thing that we built that actually pushes throughput by 2x to 3x, depending on the task type. But I want to show you that, in general, LoRAX is just as fast as VLLM, and you can obviously build many things on top of it. In terms of cost, if you were to actually do it by millions of tokens, which is pretty much how most competitors or people charge, your cost scales here by the number of millions of tokens that you query, but because you host a single deployment here and you can do hundreds of models in and out on the same GPU, your cost really is a time to generate like 1 million tokens. And then you can swing your GPU down if you don't need it further. So your cost hardly scales, even with the number of models and the number of tokens, because you're paying fixed GPU costs. So pretty nice, very useful thing to use. And in case you actually want to use LoRAX in production, it's an open source tool. We use it in production ourselves. Just involves 2 steps. you launch a Docker container where you specify the module that you'd like to run. And it does a couple of cool things under the surface that I won't talk about today. And the second thing is that you can query it via the Python client that we have through REST, and we also supported OpenAI compatible APIs. So you can pretty much do a client is equal to OpenAI and pass it a different URL, and things will work just as is, whether it's base model prompting or the LoRa-based prompting, should all work pretty nicely. Some other features we support, JSON node, one-dice inference, tensor parallelism, so for parallel inference, token streaming, CUDA graph compilation for those in the loops, just a way to optimize the forward passes. Speculative decoding, which is becoming sort of all the rage for those plugin community. We do 2 minutes, so we support that. And function calling, which should come next year as well. It's a big use case, I think, for fine tuning because we found that it's just a classification use case at the end of the day. But yeah, the function calling made us use like Mistral, the Mistral model, so on and so forth. Just to summarize, it's one of my slides. You start with the base model. You can collect data by components. Pretty much what you do with OpenAI today. You can just open for the problem. Then you can use that data to fine-tune models. And then you can serve them back to LoRAX. So it's a pretty nice life cycle, and we use it in production all the time ourselves, works really well. And so a good way to think about like how to continuously improve your models to your data. If you want to check these things out, I can go ahead and add QR codes, but both of these are open source projects that you can use. There's Ludwig.ai, LoRAX, you can go to LoRAX.ai, and yeah, thank you. We have time we have 5 minutes actually, so I know there's tons of questions. So let's just start our goal.
Super good question. When you're looking at improving Arize, I think there's a lot of talk about like fine-tuning the generation model. Like I have the feeling that actually improving the embedding model has a lot more value in there. So like what's your view like there?
Absolutely. So one of the things I've been personally thinking about is fine-tuning for that, not to replace it, but to augment it, because that's what most people have. And truth is that in any machine learning pipeline, people obviously use like these ensembles of models. So in this case, like the better, you have the de-anchor, you might have general prompting. If you always want to diagnose where the error is. If the error is at the fact that the embedding model never retrieved the right context, everything else after is never going to work. I actually think, from what I've seen, improving embeddings actually is very easy. Turns out we're going to also work on supporting it pretty soon. Yeah, and they're very lightweight, and it definitely affects your pipeline. Your RAG performance very significantly. But just to add on to that, you can fine tune for de-ranking. You can fine tune for using your retrieved context better, so it doesn't hallucinate. Like fine tuning fits into the whole story, but embedding is probably the right place to start. Absolutely. Thank you.
Hi, thanks for a great talk. I totally recognize the problem and seems like a great solution from Europe. And our customers are super finicky about data privacy and even the semblance of having grains of their data and leaking that somehow. How do you ensure that in practice these adapters are never ever leaks? And how do you talk to your customers about that? Share that.
Sorry, just want to make sure I heard the question right. Was it, how do we make sure the adapters, when we fine tune them, they don't have data leakage or bias?
The adapters are from like different tenants or different customers.
Yeah.
How do you ensure that it's like strictly separated?
Yeah, so I guess there's 2 parts to it. So there's what we do on our side to keep everyone's data and prompting separate. And then there's what you would do as an end user of the product to keep it separate. Maybe I can answer both things. So on our side, I believe like our control plane data plane are separate and everyone gets their own tenant. All the data lives there. Their adapters live there. And we do have 2 models of prompting as well in the product. Let's say there's serverless, which I think everyone's sort of used, OpenAI style. And there's dedicated where you spin up your own GPU. There's no noisy neighbor problem. It's just your GPU. You put your model, you prompt it, and that data never leaves like that tenant. In general, like we're pretty good about like data stays separate. Adapters, adapters are just weights that never like no one can access as such because it's just a request and it lives on the GPU, so it tends to stay pretty separate. In terms of like a multi-tenant serving situation, let's say you're like Notion and you have millions of customers and you want to create an LLM per user, I think it's actually at the developer level that you need to know what adapter to use and a training time to train an adapter per customer, or train like a shared trunk of general knowledge like in domain and then do a per customer adapter. But yeah, I think that like data leakage part is more on the data preparation, and that has to be done right up front. But the adapters themselves will learn what data is. Yeah. I don't know if that was not the most satisfactory answer, but yeah.
Thanks for the presentation of a good question. So in my opinion, like 80% of fine-tunings are all on the data. So do you guys have any tools or any scheduling or best practice on providing the data?
Yeah, we absolutely do. There's a lot of docs that we've written, a lot of blog posts that we have, a lot of notebooks. But I think one of the things we're also working on is a synthetic data story that helps improve your model without just staying too far away from the additional distribution, which is it's a best practice in retraining these days, not so much a best practice in fine-tuning, but it's something that we're adding, and I'm happy to point you to more docs around data preparation. But it is the most critical part of getting a good model.
Thanks for the talk, and it's really cool application multi-tenancy. Have you done enough work yet that you have data on overall cost savings or carbon reduction based on what you expect?
Yeah, absolutely. So the one thing we find is like we actually almost do like a promise these days. It's like 50% cheaper than whatever you're using in production today, whether it's OpenAI, Claude, Anthropic. It's Anthropic. And actually the cost scales. So one of the things you saw I mentioned was the historical LoRa adapter. One of the reasons we built it is that if you do faster inference, you can scale your costs to be even lower. And so we're trying to bring it down to like 30% of OpenAI spend, 20% of OpenAI spend, and it's certainly achievable for workers. Yeah.
Awesome. Thank you so much. Final note of applause for Arnav. That was a good talk. Last, technically on these talk of this room, we had so many people in this room, so thanks for being around. We have the founder of those, so get inside.
Right. You want to be able to tell that, or do you want? All right. All right. Forward, backward. If you want to use it, or you can use your keypad. Whatever.
Thank you.
Great. So,
Thank you.
yeah. So, 5:15. I'll be 5:20 max.
Okay, that should be fine. Hello, everyone. I'm Dosu. I'm Devin, the founder of Dosu. Today, I'm going to be talking about continual learning in agents, and specifically a very simple but actually very effective technique that we use at Dosu. So, what is continual learning? So, there's a few different types of continual learning within ML. There's class incremental, so the number of classes are not fixed, growing over time, and you need to adapt. Domain incremental, so this is where data distribution is changing over time, why we need to retrain models. And then task incremental, where the model is able to learn new tasks in an incremental way. For I think Voyager, anyone who has read that paper, is a really good example of kind of the North Star for agents, where it does task incremental learning very, very well. And so why is continual learning important? I would go as far as to say that continual learning is required for real-world agents. Agents are often compared to employees. So we have like AI software engineering agents, we have sales development rep agents, executive assistant agents, and like an employee, you don't expect them to come in day one, read everything, and then know what to do. Instead, someone joins a company, they try, figure things out on their own, but then they make mistakes, they're corrected, and they learn, or they run into things that are ambiguous and ask questions and learn. And I think that we have to look at agents in the same way. They're not going to be perfect from day one, but how do we build systems where they can learn from their mistakes and or ask questions and improve over time. And so, can get like onboarded within, days, weeks, months, the same way an employee would. So just a little context on Dosu, for those of you who don't know. Dosu's AI engineering team made that actually the first line of defense from incoming issues and to help automate tedious tasks. Dosu is most popular within open source to help with open source maintenance. We've been very lucky to have a lot of awesome partners, to Arize, where we've been helping maintainers maintain their projects. Everything from auto labeling, issue duplication, to actually trying to triage bugs. And as part of this, we wanted to build the kind of the world's best GitHub auto labeler. Those slides here are a little still. But basically, the challenge with labeling is that organizations have very, specific labeling schemes that are a bit ambiguous and can change over time. It's like very, it's straightforward to get a good auto labeler. It's very hard to get something that's very, very good or great. Because labels, lack descriptions. They can be subjective, especially if you give two people the same ticket, they might label it differently. And also it's organizational specific. So what we call a feature might be slightly different to what a different organization calls a feature, or like a term provider is very overloaded. Can mean different things to different organizations or engineering teams. And so we wanted to create a auto labeler as part of that learns an organization's preference over time. So kind of continuing with the employee analogy, you onboard Dosu, and then it can learn your labeling preferences and get really, really, really good over time. And so, what do you do to teach an LLM something? Well, you've got like a few different techniques. You have prompt engineering, fine tuning, and in-context learning, or a few shot examples. And prompt engineering, when we look at these solutions, we're thinking about Dosu as a product, right? So users have to do these things. And so prompt engineering is very high user effort because you have to describe your labeling scheme in detail, which requires a lot of cognitive load, and also has to be updated manually, to stay consistent. It can go stale. You have fine tuning, which Predibase obviously makes it much, much easier, but it's pretty high complexity, especially if you're talking about organizational level customization. We have end customers, we now need end models potentially. And similarly, you have to have a level of update frequency to it. So you have to retrain or refine tune models over time. And then you have two-shot examples or in-context learning, which is fairly low user effort. You just have to specify good examples of what correct labels are. It's a simple mental model, just input-output pairs. But it has to be manual, and so we really like in-context learning. And so we were like, okay, well, what if we can make these examples dynamic and continually updating? So what we call continual in-context learning, where we're able to constantly update the examples and learn from user feedback. And this was a required theme, but it's actually this turned out to be a really, really effective technique for learning edge cases with agents. Examples go a long way in demonstrating subtleties and things that might be hard to express, through words. So what this ends up looking like is a pretty simple pipeline where there's two pieces to it. One on the top is example collection. So in the background, whenever there is a user correction, we are saving that example in our example store as an input-output pair. And you can think of the example store as a traditional vector database. And then on our next inference run, we are going to find examples that are relevant, and I'll get more into the details on that later, for this run, inject those into the prompt, and then generate an output. And it almost looks like RAG, but with examples instead of documents. That's one way of thinking about it. And the results, as I alluded to, were really, really good. We've had a 30% precision improvement without any prompt engineering, right? This is just examples, collecting a bunch of data, feeding it in. But most importantly, and this is what I want to emphasize, is like it's a delightful product experience because you have this teammate employee UX where you're putting users in control. One, they can see the impact of their feedback in near real time. And it correlates the investment in the product to the quality of the product. Right? If you spend the effort to teach Dosu gets really good. And most importantly, it learns like a teammate, which is pretty cool. And so that's the good. With LLMs, things are hard, as we all know. And so what are some learnings and challenges that we faced? So with few shot examples, we quickly learned that bad examples are worse than no examples. And so what does a good example mean? We found that similar, like semantically similar or relevant examples is really important to kind of configure a good threshold for what is a good example or relevant. More examples is better as well. 1, 2, 3 examples we found were too few and would kind of overfit the model to those specific examples. And then also collecting examples that had explicit corrections was really important because this is an easy way to find like hard negative examples, things that Dosu is doing poorly on. And it avoids reinforcing existing behavior. Because if you're feeding in like examples, things that Dosu has already done, then it would just be kind of patting itself on the back. And also, it's important to keep inputs in sync. This is kind of a subtle thing about production, but in this specific case, people edit inputs a lot. So making sure that you're syncing both the inputs and outputs when you get corrections. And so this is just the beginning. We chose auto labeling also to talk through because it's really straightforward. It's like a classification task. So success is really well defined. It's really easy to collect feedback, but this we're excited about applying this to other parts of Dosu. So an example is learning response preferences or tone of voice for replies based off examples. Applying it to retrieval and re-ranking. So we were just talking about fine-tuning a model for re-ranking. Can you use examples as a way to learn how maybe Dosu should re-rank results in the future? And then the challenge on the product side is how to organically collect feedback from users where you can get these corrections or these examples. And then there's also interesting things around maybe writing custom prompts, having Dosu maintain its internal learnings as written rules, not just examples. And we're also fans of GSPy, and I think there's a lot of interesting optimization. It's probably a very open-ended research problem about what is a good example, what is the best set of examples to show for in-context learning. And one last thing is this is only possible now because context length of models have grown so much that we're actually able to shove a lot of example information into prompts in a way that previously you would have hit token limits very, very quickly. So it's like an interesting side effect of longer context model lengths that we have today.